Hello and welcome to another physics lesson. Today we're going to look at torque some more. We're actually going to try to do some math with that, actually do some problem solving. So we'll review a few things with torque and angular motion, and then we'll get into it. So in my last presentation, we got Newton's second law applied to torques, and so we got that net torque is equal to angular acceleration times the moment of inertia. And we talked about how that's a parallel to Newton's second law of net force equals ma. And so you might recall whenever we do a second law problem, I always advocate doing two equations, the actual second law equation, and then also write out one that does the sum of the forces. So adding all your positive forces and subtracting your negative ones. And so in this case, we'd be dealing with torques. So we'd be adding all our positive torques and subtracting all our negative torques. The one thing to remember is our convention for directions with angular motion is that clockwise is traditionally our negative direction, and counterclockwise is traditionally the positive direction. That's how that traditionally goes. I suppose if you wanted to, you could always kind of fall back on my convention that I like to use for a linear. I mean, this is a convention, so you don't have to necessarily follow it. So you could say, hey, I'm always going to, if I know the direction of acceleration, I'm going to make that positive. That's kind of what I like to do because I end up with fewer weird negatives. Also remember, because a lot of times we end up with these situations where we'll have to take linear information and translate it into angular. So remember to do that, we're just dividing by the radius. So angular acceleration is going to be the linear acceleration divided by r. And angular velocity is the linear velocity divided by the radius. So the problem I came up with is this. And before I get into it, realistically, if you're bold enough, you could possibly just stop watching right now and go do the homework. But I'm going to work through a sample problem. And this problem is actually on the homework. And it's kind of hard. So you might want to stick around. It's up to you. I'm also going to give some hints here towards the end on one of the other problems. I'm just going to kind of draw the picture for you and get you going on that. So in this situation, what I've got is I've got a car that is accelerating. And so it is going from 0 to 30 meters per second in 3 seconds. The mass of the car is 1,600 kilograms. It has wheels of 27 kilograms and a radius of 31.5 centimeters. I want to know what torque acts on the wheel from the engine. And so here's my picture of what's going on. There's my car. We've got a force. The important thing to realize here, I'm kind of assuming a rear wheel drive vehicle, is that this wheel is going to spin clockwise, the way I've drawn it, so that it can push back on the ground. Now remember that gives us a reaction force of the ground actually pushing forward on the car. And so we have these forces acting on our car. We have force normal, we have force gravity, and we have a forward force of friction. I'm ignoring friction from the front wheels from right now because this problem was hard enough as it was, and it just didn't occur to me to put it in there. So we'll just move on. So that then gets me to this wheel. Then we're going to have a torque from the engine, and it's not, we'll just call it torque from the engine to keep things simple. We won't worry about what all is going on behind the scenes. And then we have torque from the friction. And so friction here, you can see, is going to be a counterclockwise torque. I'm going to make that positive. And the engine is a clockwise torque. So I'm going to make that negative. And you can kind of see that doesn't really make sense because we know that there's going to be a net torque in the clockwise direction. So I'm going to end up with weird negatives, but I want to stick with the traditional because that's how I made my boards. The torque from the friction is going to be the force of friction times the distance, which that distance is going to be this r, so I'm going to rewrite that as so. And we have our net torque equation of second law equation, or alpha times I, and then our sum of forces. So we have torque from the friction. So can we see that? Okay. We have torque from the friction is going to be my positive minus the torque from the engine. I actually went ahead and did a similar thing here for the linear. Since we do have a linear acceleration, we know that we have a net force is going to be equal to the force of friction from the road on the car. So there's my sum of forces. There's only one force, so the net force is that force. And we also have the net force equals ma, Newton's second law. All right, next board. Obviously I'm going fast. Pause as you need to, look it over, rewind. But I have 4 boards to get through. So lots of stuff here. Let's take a look. So there's second law again. Force friction equals ma. I need the acceleration. Now I have the information I need to get the acceleration. It's going to be delta v over t. So we'll plug those in. 30 meters per second. Now I started at 0 and from 0 to 30. So my delta v was 30. Over in 3 seconds, that gives me an acceleration of 10 meters per second per second. Force friction then is going to be equal to, since it is my net force friction is my ma, the mass, which was 1,600 kilograms, times the acceleration we just got of 10. That gives me 1,600. And this is when I realized, hey, wait a second, there's actually 2 wheels on the back of this vehicle. So that's actually 8,000 per wheel. All right. So then we get to our torque. Our torque is going to be that force friction we just found, 8,000, times the radius that we had back on the previous board. And so we do that math. Now the radius does have to be in meters. We always go to meters in physics, or when in doubt, go to meters. Sometimes it doesn't matter, but if it matters, it has to be in meters. So we convert that to meters, and I do that math, and I get that my torque from the friction is 2,520 Newton meters. Going up here, I have my net torque equation from the previous board equals alpha I, and my sum of torques. And so I'm just going to set those equal to each other. So we have this equation right here. And then what we're going to do is we say, well, I need to know alpha. How do I find alpha? Well, I know acceleration and I know the radius. And so I can use that alpha equals linear acceleration over the radius to give me my angular acceleration. And so plugging in the 10 and the 0.315, again, meters, convert it, and I get 31.7 radians per second. Notice I snuck a little negative sign up there because that is a counterclockwise acceleration, which means it's in the negative direction. I also need to know what my I is. Fair or unfair, I decided to keep it simple and just model it like a disk. Probably not really a disk. Anyway, the moment of inertia for a disk is 1/2 mr squared. So we plug that into our equation that we now have alpha times, so we had alpha I here, now we have alpha times 1/2 mr squared equals torque from the friction minus torque from the engine. Now I have some of those numbers already, so here it is plugged in, everything that I know. So my angular acceleration in for alpha, negative 31.7, 1/2. I know the mass is 27. I know the radius is 0.315. Once again, we're in meters. And then there's the 2520 that I got from over here. And so I get that the torque applied to each of the rear wheels is 2,562 Newton meters. All right. I hope that made sense. I hope that's helpful. One more board. It's not as busy. So this can be applied to an object falling over. So if I simply had, say, my whiteboard marker and it fell over, there is a torque that's making it fall, making it accelerate, have an angular acceleration. It's rotating about the tip. So we just have this thin rod rotating about the tip. The thing that I thought you might need some help on is figuring out this torque equation. So what I have is I have a rod of some length L. It's going to have some mass M, which I didn't draw on here, but we'll say it has some mass M. And we can treat this, if it's a uniform beam, a uniform rod, as if the mass is all centered, located right at the center. And so that's what I've done. There's my center. We'll come back to that in a minute. So as this tilts, gravity is going to be straight down, and there's going to be some distance x from where it's kind of pivoting right there. So there's my pivot point, or some distance x from that. So the basic way I'm going to deal with that is there's my lever arm, because remember, my lever arm and my force must make a right angle. So there's my right angle. There's my force gravity. Now I don't want to mix things up here because those are all distances. So I don't like to draw both distances and forces on the same diagram. That leads to tears. At any rate, this distance then is going to be my lever arm for that force. These two things are at right angles. So there's my lever arm. That's what I need. I need that if I have a vertical force, so I need a horizontal distance. All right. Now this hypotenuse is actually going to be 1/2 L, because I am just going this distance right here. Gravity is acting, or this object behaves as if all of gravity acts right there at the center. And so, because it's uniform. And so now I have my torque equation, torque equals force times distance. That's going to be my distance. You can use trig to find that. Gravity is my force. You should know how to find that. I'm not going to do more, or I'm not going to do more of it for you than that, but hopefully that will help get you started on the problem that involves a falling rod. If you have any questions, as usual, please send me an email, and thanks for watching.